Hello everyone, I'm sorry this talk will be in English. Hello, I'm Nikolai, co-founder of Streamroot, and I'm here today with Jordan, our lead backend developer, to tell you how we were able to deliver 1 terabit per second of video data through our peer-to-peer assisted network during this World Cup, football World Cup in this summer. Of course, it's a little bit less than the 3 megabit per second from the previous talk, but here, in our case, it was done without using a single server and only in peer-to-peer. So just to give you a little bit of context, Streamroot is a 5-year-old company founded in France, and we provide a peer-to-peer assisted video delivery technology that helps media groups, TV channels, and any large VOD or live platform to improve their video delivery over the internet. So unlike fully peer-to-peer networks like BitTorrent, for instance, we have developed a hybrid technology that works in tandem with the broadcaster's edge servers or CDN workflow. And we have today developed one of the biggest and largest peer-to-peer networks on the market, and we serve more than 20 million video sessions per day through our technology. We have customers all over the globe with, for instance, Russia Today, Canal+, Eurosport, Dailymotion, and some others. And before going into the details of how it works, here are a few advantages of using a peer-to-peer assisted delivery solution like Streamroot. So first, because you're able to get video segments from sources that are closer to you, you're able to improve the quality of the distribution of the service. Broadcasters that are using Streamroot usually see better bit rates on average for the users and lower rebuffering rates. Second, we're able to scale the video distribution almost infinitely as we don't use any servers. And this is extremely important, of course, when you have to stream for a huge audience with huge spikes like the World Cup. And finally, we're able to reduce the bandwidth costs for the broadcasters up to 75%, which can be, of course, a lot when you pay for the bandwidth. So how does Streamroot work in practice? Imagine you're watching the final of the World Cup with 1 million other people watching it at the same time. With a traditional CDN system, every user will get the video segments from either a central server or a group of edge servers that are centralized. With Streamroot, what happens is that you're able to both get video segments from the CDN and from other peers who are watching the same stream at the same time. And so in practice, when you connect to the web page or the application, with Streamroot you will at the same time start downloading the first video segments from the CDN and also connect to our backend that will return you a list of peers that are watching the same content and that are optimized for you in the smart way that we'll talk about a bit later. And so when you receive those peers, you're able to connect with them directly in peer-to-peer with the WebRTC data channels and start exchanging video segments with them, which will offload the traffic from the CDN or the server.
So, thank you. So, as Nikolai mentioned, peer-to-peer connections uses a technology called WebRTC. So, let's cover the basics of how to set up a WebRTC connection. So, imagine we have a couple of devices, and we want people watching the same stream to... Can you? Yeah? Oh, okay. Yeah. So we want people watching the same stream to exchange video fragments. So it's clear that we need some kind of service that knows and remembers which stream each peer is watching. So we'll call that the tracker. Now, for some reason, and one of them being security, peer cannot connect directly to each other. There need to be some kind of agreements, some kind of handshaking. So those agreements messages are exchanged through a service we call the signaling service. So the WebRTC norms doesn't say much about the signaling service, but at Streamroot we implemented a WebSocket server. So so the signaling server just relays WebRTC control messages. So now that both peers finally agreed to send and receive data, then the video fragments can be delivered. But as anything involving the network, it's not that easy, and there's two things to consider. One of them being NAT, and the other is firewall. So let's start with NAT. So the question is, how does a peer, which usually sits in a private network like at home, how does the peer knows his public IP? So to answer that question, he would just ask a remote server, and then the server would reply with a payload containing the IP address and the port it has just seen. So at Streamroot, we don't have to run our stun server because like internet giants like Google or Yandex, they already operate stun servers publicly. So the other question is, the other problem is a firewall. So most peers are behind some kind of a firewall, and the question is how to let incoming connection through. The thing is, once the peer contacted the stun server, it has already created a hole in his firewall because his firewall has to let the response packets in. Now, because it's UDP packets and that because most consumer-grade firewall are kind of cheap, any incoming packets on that port are allowed to come in, and this regardless of the origin. So if you want more detail on this, you can watch the good talk by Alexander Topol that he gave a couple of months at HighLoad Siberia. So now that we've covered the networking connectivity, let's talk about the matching process. That is how to find good peering candidates for any given peer. So of course, both peers must watch the same video. But then for VOD, as opposed to live, the peers must be more or less at the same position in the video. So that's because video players, they only download and save a couple of minutes worth of video in their buffers. So for instance, if a peer is at the beginning of the video, it cannot get segments from a peer that is at the end of the video because the peer at the end doesn't have the segments in its buffer anymore. So now imagine we have a very popular stream, so thousands of viewers and thousands of potential sources. We need to score each of these sources to select the best one. So at first we considered a score based on geographical information, but that didn't yield a good result. So we think it's because the GeoIP information, they are not really accurate, and also because how the networks are interconnected, it's not because two peers are physically close that they have a good connectivity between them. So now these days we mostly score based on network topology proximity, and in particular we favor matching peers that belong to the same ISP. And this way, we are also friendly with the ISPs because we limit the peering between the ISPs.
And so we're doing the original matching on the server side, but we also have multiple client-side algorithms to improve the efficiency and also have better peering between the different peers. So for each segment of video, to do the peer-to-peer sharing, we actually split each segment into small chunks of 60 kilobytes. And in that way, we're able to download one segment of video from several peers at the same time. And this is very useful to us because it allows us to actually measure and estimate the bandwidth between a user and each of his peers separately. So for estimating the peer-to-peer bandwidth, we actually are using a TCP-like bandwidth estimation algorithm. So basically, for each video segment, for a specific peer, we ask more and more chunks from that peer until we start seeing some packet drops, and then we very quickly back off to basically know that the limit for this peer in terms of bandwidth will be around just before he drops the packets. And so with this, we're able to rank the different peers a user has with metrics like this bandwidth estimation, but also with other ones like RTT, latency, packet drops, and some others. And we're able to rank those different peers between themselves, and every few minutes we are recycling the peers a user has by removing the bad ones that have a low connectivity and bad connection and replacing them with new peers from the backend. And we saw that doing that improves a lot the overall peer-to-peer efficiency, and at the same time it also reduces the need to ask the backend for more peers too many times, and basically creates a distributed matching system. So we are using other optimizations on the client side, but for the sake of time, I'm only going to mention two of them. The first one is the dynamic resource adaptation algorithm. So basically, a long time ago, we saw that when we do peer-to-peer streaming, there is always a very small population of users that has like very bad quality of service performances like buffering, drop frames, etc., etc. What we saw is that it actually happens not only with peer-to-peer but also without, and it's most of the time linked to the fact that the user has very bad hardware, like not enough CPU or not enough memory, etc., etc. So seeing that, we implemented an algorithm that will be watching in real time all the different quality of service metrics for each user, like for instance the buffering rate, the number of drop frames, or the battery usage for mobile phones. And as soon as we see any of those metrics performing unusually high, we basically start to reduce the peer-to-peer, some of the peer-to-peer parameters that we have. For instance, we reduce the number of peers a user is connected to, or the upload limit speed that he can have. And if it still doesn't work, we reduce it more and more until we don't have any more peer-to-peer at all, and the user just gets everything from the CDN. And so this improvement helped us first to actually improve the peer-to-peer and the quality for the delivery, but even better, it allowed us to make sure that we never degrade the quality of the streaming with peer-to-peer, because in the worst case, you just have the same quality as you would have with just the CDN. Another optimization we did is the superseders for live streaming. So the superseders concept has been around for I think since the beginning of the peer-to-peer systems with like Email and Casa. And so the concept is pretty simple. For live, you always need a part of the users to be seeders, meaning that they will download the segments from the CDN and share it to other peers. So you can start a peer-to-peer cycle, basically. And so, of course, you want the peers with the better upload capacity to be the seeders, so they can share not only to one peer, but to many peers, and basically have more and more peering afterwards. And so we implemented a distributed algorithm that does exactly that. It is ranking the different peers by upload capacity, and then it elects in a distributed way a part of the peers, around 5%, that become superseders and will seed the different content to the other peers. And that also was one of the great improvements that we were able to implement into our peer-to-peer solution. And so, as I mentioned, we were lucky to be able to do the Football World Cup with several national broadcasters in France, Europe, and also South America this year. And so before going into how we scaled to that, I'm going to give you some general numbers about the scale of this Football World Cup. So this Football World Cup has been extraordinary in many ways. First, of course, because it was hosted here in Russia. Second, because as we're a French company, we were very happy that France won its second championship this year. And third, we saw more users connecting and watching the games online than ever before. To give you an idea, Akamai, which is one of the most used CDNs in the world, had a peak of 22 terabits per second during this event, and that was more than 3 times more that they had during the 2014 World Cup 4 years ago. And so here are some numbers we achieved with our peer-to-peer solution. So first, we were able to stream almost 70% of the traffic for the broadcaster, for our customers, which means that they were able to divide by more than 3 their CDN traffic thanks to our solution. Second, we were able to have a peak of more than 1.2 terabits per second of delivery through our peer-to-peer network, which again, to give you a comparison, is more than 5% of what Akamai delivered this year during their peak. Third, we had huge traffic peaks in terms of number of concurrent users. We had some games with more than 600,000 concurrent users on the same stream, and that was something that was difficult to handle for us in terms of on our backend and tracker, as we'll talk about it a bit later. And finally, as you can see on the graph on the right that represents the traffic, the CDN and peer-to-peer traffic during a game, we also had to handle very, very big spikes at the beginning of the games, with sometimes thousands and thousands of users arriving at the same time in 1 minute. And so to show you how we faced all the scale and volume, we had to do a lot of improvements on our backend. And so I will let Jordan now present you our scaling journey during these past few years.
So let's now focus on how we approach the scalability challenges. So at first, we started with this basic architecture. So you can see that any viewers could connect to any servers, and that we relied heavily on Redis. And this worked well until we reached the 50,000 concurrent viewers mark. And at that point, we started to see some issues with memory management in Node.js. And also Redis started to become a bottleneck because we didn't use Redis cluster at that time. So in 2016, we had to rewrite everything from scratch and to make some major architectural changes. So first, we replaced Node.js with Go, because we thought that Go was performant and that it was easy to learn and easy to write concurrent code with. Then we decided that we wanted to get rid of a central DB, so we decided to do only in-memory computation. So this in-memory property required a change in our load balancer strategy. So we wanted to make sure that 2 peers watching the same stream would end up in the same tracker. So we decided to shard the viewers by video ID. We also replaced HA proxy with Nginx because we thought it was easier to do load balancing with sharding and consistent hashing with Nginx. So in the end, we ended up with the following architecture. And it worked well for a time, and it provided very good scalability, and we achieved some pretty interesting numbers with that. But this architecture has a major flaw, and I'm pretty sure you can see it by now. So the problem is with when we have like very, very popular streams, so let's say more than 500,000 viewers watching the same stream, then a single tracker cannot handle that many peers. So as we were preparing for the World Cup, we had to come up with a solution. So we introduced a new service in our backend, and this new service is called the router. So the router is in charge of routing each peer to the correct tracker that it should use. So let's go through an example. So let's say that the first 2 peers join, and then the tracker then the router tells them to use tracker 1. Then the next peers join, and so on, until a certain threshold is reached. And at that point, the router starts to send the new peers to another tracker. So we use Redis to count the number of viewers. And when viewers disconnects, so when he leaves the stream, then its tracker updates its peer count in Redis. So for now, we don't use a Redis cluster. So it's a small limitation, but it's not that bad, because if Redis dies, then it will be quickly restarted. And then in the meantime, new peers that are watching the same stream, they will end up using the same tracker. So that's what we wanted. It's still correct. So now that we've talked about scalability, let's talk about autoscaling. So this is a screenshot of one of our customers' dashboard. So you can see a typical traffic pattern with a lot of viewers during peak time, so at 9 p.m. when people are watching a video at home, but we have very much fewer viewers during the night. And most of our customers, they have this kind of traffic pattern. And besides, many of our major customers, they are more or less in the same time zone. So their peak time is synchronized. So for us, it would be very costly to scale based on the peak demand. And so for us, autoscaling is a must. But fortunately, autoscaling is not that hard today. And we use Kubernetes, we leverage Kubernetes for that. So our services are running inside containers, and the containers are managed by Kubernetes. So here's a simplified version of our current architecture. So we are running with Google Cloud. But do note that we are actually using 2 tiers of load balancer. So the first load balancer is only performing the TLS termination, and the other load balancer, Nginx, is actually doing the sharding by video ID. For resiliency reasons, we run rather small nodes, so 4 cores and 8 GB of RAM, but we run many of them. So we run our containers as a daemon set, so that all of our nodes have more or less the same usage. And we've set the target CPU utilization to 70%. So when the load increases, then a new VM is started, the containers are started, and the load balancer starts to send some request to that node. So in practice, this has been working very well for us. And this graph shows the number of servers that we have in one of our regions. So as you can see, the capacity follows closely the actual usage, so we don't have a lot of over-provisioning. But the autoscaling is not perfect. So as we were preparing for the World Cup, we expected that just before the start of a game, we would have thousands of new viewers per second. And the thing is, the autoscaler is not fast enough, because to detect an increase in the load, then to start a new VM, to install Kubernetes, start the containers, and wait for the health checks to pass, all of this takes around 5 minutes, and this is more than enough time to overwhelm a single node. So for the World Cup, we had to over-provision a little, so we used bigger than usual nodes, and we lowered a bit the CPU target utilization. So in the next slide, I will dig into some Kubernetes pitfalls and give you some tips. So, but first, at Streamroot, we are a rather small organization, so we only use parts of Kubernetes. For instance, we are not using the role-based access control. We don't use the quota neither, because we are a really small backend team. The same, we don't use the horizontal pod autoscaler, because we autoscale a bit differently. And we don't use the advanced scheduling mechanisms, because we use daemon sets. But what we like with Kubernetes so far is that it's really trivial to roll out a new version of our services. Then it really simplifies resiliency and failure management. And finally, service discovery is really easy. So now I'll talk about some pitfalls. So the first advice I'll give you if you're running Kubernetes with a HighLoad would be to mind the network path. So for example, let's go through the path a packet would take when it comes from the internet to one of our tracker. So at first, the packet arrives to the first load balancer, then it should be sent to Nginx. But in fact, it's not directly sent to Nginx, it is sent to the Kubernetes Nginx service. So a Kubernetes service is actually a virtual IP that makes a set of containers accessible to the outside world. But that virtual IP is using IP tables and NAT, which could mean an extra network hop this way. So once the packet arrives to Nginx, it is sent to one of our trackers, but that correct tracker might very well be on another node. There's one last thing to know is that by default, the containers, they run inside an isolated network namespace, which means that sending and receiving packets involves some routing that is between namespace, and this routing is performed by a virtual switch inside each node. So when we started with Kubernetes, we saw that almost half of the CPU time of our node was spent in kernel land and dealing with software interruptions. And it was a bit frustrating because we thought it was not actually our code that was running, but the server was were just busy dealing with packets. But fortunately, we found some optimizations. So the first optimization is with the Kubernetes service. So we now run them with the external traffic policy local configuration. So which means that configuration means that the kube proxy only forwards the external traffic to a local pod. And this way we can avoid an extra network hop. And the second optimization is with Kubernetes pod. So we now use the host network equal true configuration, which means that the containers, they directly bind to the host network interface. So this way we avoid the extra routing between the network namespaces. But those optimizations have some caveats, and the first one only really works if you're using daemon set, because otherwise the traffic could be imbalanced between the nodes. And the second optimization has some security implications, because it's not always a good thing to make your containers directly accessible to the outside network. So, but for us, these optimizations brought around 20% more requests per second, so it was worthwhile. And there's another issue we run into with Kubernetes, and it's related to connection tracking. So even with this annotation, this configuration, network address translation is still performed, and connection tracking is still required. So if you are having a lot of concurrent connections, be sure that to tweak this kernel setting, because if you don't, then your connection tracking table could be full, and then you get these kind of messages in your log, and that's a guaranteed outage. At Streamroot, we implemented this kernel tweak that I just mentioned with yet another daemon set. So the /proc file system of the node, of the host, is mounted directly inside a privileged container, and that container applies the correct sysctl command. So as you've noticed, we are pretty big users of Kubernetes daemon set, and this could be a bit unusual with Kubernetes. So let me explain the problems we had with deployments and replicas. So our first problem was that we have some services that are very busy, that handle a lot of loads, but we have some other services that mostly do nothing. So depending on the pod's placement, we ended up with some node being very busy and some other nodes doing mostly nothing. So it was a bit problematic. And the other problem with the deployment is that sometimes several copies of the same microservice could end up on the same node. So for instance, in this example, if node 2 dies, or if the autoscaler decides to remove node 2, then we have twice as many viewers that will be disconnected from the tracker, and they will have to reconnect to another tracker. So of course, this can be solved with pod affinity and resource requests. But we found that a daemon set was just easier to manage and to deal with. There's one final optimization that I'd like to share, and this time it's a client-side optimization. So to deliver 1 terabyte of peer-to-peer traffic, it requires around 250,000 WebRTC messages per second. So that's a lot of traffic. And as you know, the cloud provider, they are super expensive when it comes to internet traffic. But we found out that the WebRTC messages, they are actually kind of verbose. So we decided to remove the part of the messages that we didn't want and to compress the rest using a protocol buffer. So this yielded a 10-time reduction in our signaling bandwidth, so which meant some nice cost saving. As a conclusion, I'd like to say that the key to scalability and resiliency for us was really to keep it simple and to stick with the usual patterns. So as I've mentioned that we are using horizontal scaling, we do load balancing through sharding. We try to limit the shared states, and also protocol compression is always a nice option to consider. So the next steps for us will be to consider multi-cloud for resiliency and independence reasons, and to try to have a more reactive auto-scaling. Thank you for your attention, and if you have any question, please let me know. Thank you. Yeah? Yes, I guess.
Hi, my name is Oleg, Facebook. Thank you for the presentation, very interesting. So first things first, I cannot not mention that the part with peer-to-peer looks exactly like Pied Piper from Silicon Valley. So I'm sorry, yeah. I cannot not mention it.
We were
first.
first.
So the question is, how can you actually convince users, like for example myself, I install the application, that I should pay for outgoing traffic to serve basically your needs and not my needs?
So there are different answers. The first one is that actually by using WebRTC, the good thing for us and for the broadcaster is that you don't need to convince the user because it's completely transparent for him. So he doesn't have anything to install, like no plugin as you had to do before, like a Flash plugin or something like that. So that's the first answer. And the second answer, which is more for the user, is that by using the peer-to-peer acceleration delivery, you're able to have a better quality in some cases and like be more resilient to central server saturation. And so in the end, you have a better quality, even if you're giving up some of your bandwidth to like the system. So if the user can have like better bit rates and less rebuffering, I think most of the time they agree to use a peer-to-peer solution.
Thanks.
Hi guys. I actually have something to add to this question because I have a list of questions that arise from the previous. The previous guy was talking about the latency. The previous guy was talking about the battery power of the users who are using mobile devices, and I guess that it greatly suffers with this solution. Make me wrong if.
Yeah. Well, OK is also using peer-to-peer. So for latency, indeed, if you have a very low latency, which means less than 5 or 3 seconds, it's very difficult to do peer-to-peer. On our side, we have customers, I think, like Canal Plus, they have 10 seconds of latency, and we're still able to achieve 35% of peer-to-peer offload with that. So, of course, the less latency you have, the less peer-to-peer you will be able to make. And what was the second?
Well, actually, let's talk about the latency, because the guy was concerned about just as few as half a second or maybe 100 milliseconds, and you're talking about the latency of 10 seconds, and that's, well, if people are watching with 10 seconds latency, I guess they don't care about the extra latency that you provide. The second question was about the battery power. If the guy is using, well, if the end user is using the mobile device, and it's actually a concern for the одноклассники who was speaking before you. And I guess that, without the consent of the user, you are using his battery power.
For the mobile devices, first thing is that we don't activate by default peer-to-peer upload on cellular or 3G or 4G networks, because the data can cost to the user, and we don't want that. But if they are connected on Wi-Fi, we still are able to do a peer-to-peer sharing for those users. And as I was explaining in one of the slides, we have implemented for mobile and actually non-mobile devices too, we have implemented algorithms that check the usage of the CPU, of the memory, of the battery. And we make sure that we don't exploit this usage, and that if we see that some users don't have enough CPU or memory or battery, we basically stop doing peer-to-peer. So we have something that adapts to each user in terms of usage.
I actually have, if I may, a couple more questions. When you were speaking about the NAT traversal, the одноклассники guy, he mentioned in his presentation an article that they wrote about a couple of weeks ago about how they are doing this, and it's much more difficult and much more complex. And even with all this that they are doing with it, it's quite sophisticated sometimes, quite simple sometimes, but they can traverse more than, if I remember correctly, 86% of NATs. More than, I mean that at least 14 NATs still do not traverse.
You mean that not everyone is able to connect?
Because, say, some NATs would change the end port. You mentioned that you get the end port, and this end port answer will be say, as different every time. There is an algorithm sometimes where you can project that and somehow calculate the end port that will be next.
This is, if you're more interested in the subject, there was a conference by Alexander Topol a couple months ago about it, and it doesn't always work. That's true, but most of the time it's okay.
The question was that you are using on your slide you had just one simple.
No, I wanted to.
I guess that was for illustration, and you are actually using more sophisticated.
Yes.
But in our case, I think we have less than 5% of users who can't connect and who can't establish a connection. But for 95% of them, there are no problems basically.
And okay, if I may. Who does the decoding, transcoding, say, if we have several users who are on the same page, as you mentioned, they have to be on the same page, not just in terms of where they are in the video, but every other aspect. They have should have the same aspect ratio, they should have the same bandwidth to make this transaction between them meaningful. And how you do this? Who does the transcoding if it is necessary?
So we don't touch the transcoding part or the packaging or the encoding. That's all done on the streaming server or on the origin server.
They have to be actually on exactly the same page.
Yeah, and so then as Alexander explained in the last talk, you have basically different bit rates for each video. And on our side, we will connect users with people who are watching the same bitrate. And if you change from one bitrate to another, like after 30 seconds, what will happen is that we have actually different peer pools for each user for each different bitrate. And so either you will reconnect to other peers who are like on the bitrate above, or you will just re-ask some peers from the backend that are on this new bitrate.
That was the next question you already answered. Thanks.
Thank you. Another question? Yeah.
Hello. I have a question about how you using peers inside your platform. So when user connect to your platform and watch one streaming, and he have a powerful PC, for example, you're not using his PC for delivering another stream. I mean, in the same time. So if he is super peer, you can use his PC for deliver different stream happens in the same time.
We could do that, but we don't.
Yeah, we don't
Why?
want.
Why?
Yes.
Well,
Mostly because I think we don't want to use the resources as we were saying. We don't want to use the resources of a user if it's not helping him. So we're just sharing the content that he's watching, basically. And if you, for instance, are watching a live stream or a VOD stream, and then you disconnect and you just close your browser or your tab, you disappear completely from the peer-to-peer network. We don't do like any caching on the computer or anything like that. We try to be as transparent as possible for the user.
Okay, thank you.
over there.
Does the user opt in for peer-to-peer, and can he opt out? I heard that you're not using peer-to-peer on 3G, etc., but can he opt out on Wi-Fi or other devices?
So we provide basically an API for that, but that's the choice of the broadcaster who is using our technology. So some of them have, actually most of them don't do opt-in, they do opt-out. Some of them don't do opt-out. Some can, you can either install, like, I don't know, a checkbox in the player settings to remove peer-to-peer or not. But we at least provide the API to do it either on the client side for each different client with an API in JavaScript, or on our dashboard on the backend side, where you can just remove peer-to-peer for like all the users simultaneously, for instance.
Thank you.
Another question, maybe?
Last question.
How much you increase your resource by migration from Node.js to Go?
How much did we save? That's a good question. Actually, I was not here when the stack was based on Node.js, so I cannot answer specifically to that problem. But I think Node.js today would be very fine. But there's the language and what you do with the language, and I think we made some mistake with Node.js at that time. So there is, it's not. I don't want to say that Node.js is bad, but yeah, with Go it was much easier, I think, to do. The code gets simpler.
I think I remember it was like 3 years ago, so it was a long time ago. But our first servers were able to only handle like 1,000 concurrent users, or like maybe 5,000, and we did at least 10 times more with Go. But it's not just because of a language, as Jordan is saying, it's because we did other optimizations too. All right, here.
Hello, can you tell what server decision or application do you use to stream to first receivers? For example, all receivers has bad internet, 3G, and what server decision do you use to stream to them, to the first clients?
Let's say that our solution is a hybrid solution, which means that at the beginning, every user will actually get the segments from the CDN, whatever happens, because we don't want to add any latency or have a bigger startup time for the video frames. So basically, at the beginning, everyone is streaming from the CDN, and then we do the matching we try to optimize when we have enough users. If you only have 10 people watching the same stream, they will, of course, all connect together, even if they are not on the same ASP or even if they don't have the best bandwidth possible. But then if you have 1,000 or 1 million users, then we're able to better select the different peers for each user to optimize the bandwidth for each of them. I don't know if it's clear.